Hello students, in last class we have talked about definite integration, indefinite integration, and we understood that definite integration basically gives us area under the curve, right, and indefinite integration gives us a function whose derivative will be our original function, right. So, we will see some applications, we will start with few examples based on what we learnt in last class and then we will continue, clear. So, students, let us see these questions now. So, here they have basically given us the speed versus time graph, right. So, you can see that mentioned here on the y axis we have speed in meter per second, on the x axis time in seconds. So, they are asking us to find out the distance covered. So, whenever this case is given to us, we know that this particular scenario the distance covered can be easily calculated by just looking at area under the curve, right. We can directly find out this area and this area even without integration, correct. So, that is what I am going to do. I am not going to integrate this expression, I am just going to find the area under the curve. So, if I need to find the distance covered in the first 5 seconds, that would be this area. If I need to find the distance covered in the next 5 seconds, that would be this area, correct. And if I need to find the distance covered in the overall 10 seconds, I will add the total area, I mean this area plus this area, correct. So, we can do that. So, let us first find out, let us write the total distance itself. So, distance travelled in 0 to 10 seconds. So, that should be equal to, so first in the first 5 seconds it travels this much. So, which is this length is 10, this length is 5. So, that would be 10 into 5 which is 50 meters plus on this side I can divide this into 2 parts, correct. So, this is once again a rectangle and this is a triangle, we can easily find the area. So, this is once again 10, 5. So, 10 into 5 is 50 meters plus, so this is for 0 to 5 seconds and this is for 5 to 10 seconds. Okay, so what is the remaining triangular part area? So, this base is 5, 10 minus 5 is 5 and this height is 20 minus 10 which is 10, right, and we can directly apply half base height. So, that is it. So, simplifying this will give me the value. So, 50 plus 50 is 100 and this would be 25, right. So, 125 meters will be the distance covered in this scenario, clear. Okay. Now, similarly, let us see another situation here. So, here you can see that the speed is varying as a function of time in a sinusoidal manner. So, it is a sine function, clear. So, we call it as a sinusoidal function. So, sinusoidal. So, any function which is basically in the form of sine theta or cos theta. So, all these are called as sinusoidal functions, clear. Okay. So, now obviously we can't do the earlier scenario, I can't just shade this area and directly tell what the area under that curve is, right. I do not have a formula for that. So, I will definitely have to integrate to find out how much area is present under that curve, and we know how to integrate, right. We all know that area under the curve is nothing but integral of this v into dt. In this case area is nothing but distance. So, the relation between distance and speed can be understood in this manner. So, we have discussed this earlier also, integral of v dt will give us distance covered. So, that is what I am going to do. Obviously, I will have to substitute the limits. So, here you can see that this is 0 and this is pi seconds, pi 22 by 7, right, approximately. So, let us do that calculation now. So, in this case distance will be equal to integral of, I will just substitute the function that they have given for v, which is 10 sin t, correct, into dt. So, observe that I have just written integral v dt, clear. Now, if I integrate this I will just get a curve, but what do I need? I need to find the area under this, right, I need to find the area under this. So, if I substitute the limits I will have to perform definite integration to find out the distance covered. So, in this case this will be equal to, so distance covered in 0 to pi seconds is what I am trying to calculate here. So, to find that I will need to integrate this and substitute the limits. So, first I will bring 10 outside and integral sin t dt. So, this is something which you all know, integral of sin t into dt. So, what is the value of that? So, do not make the mistake of substituting it as cos t, it is not cos t, it is minus cos t, correct. So, minus cos t, actually we should write a plus c, but anyways I am going to perform definite integration here. So, I am not going to worry about that constant term. So, 10 into minus cos t. Now, I will substitute the limits. What are the limits I am looking for? Time varies from 0 to pi seconds, right. So, 0 to pi, and when I calculate this I get 10 into, let me bring this minus sign also outside. So, minus 10 into, now we have a cos t inside, right. So, I have a cos t inside. So, first I will substitute cos pi, I will get cos pi, then after substituting 0 I will get cos 0. So, this would be cos pi minus cos 0. Now, you just substitute the values minus 10 into, so cos pi is minus 1, which is cos 180, right, minus cos 0 is 1. So, that is it. So, simplifying this will give you the result. So, minus 10 into minus 2, which is 20 meters, right. So, that would be the distance covered. So, in that manner, whatever is the speed given to you, you can directly calculate the distance covered by using definite integration. Clear? So, students, let us understand further about this sine function. This is cos function. So, this is y is equal to cos x. So, a general function, I am not taking it in terms of time. So, I am taking a general function which is represented by y is equal to sin x and y is equal to cos x. So, this is how the graphs would look like. So, this is the cos graph and this is the sine graph. You can see that sin 0 is 0, this is pi by 2, which is 90 degrees. So, at pi by 2 the function will be maximum, which is 1. You all know sin 90 is 1, right. And once again sin, this is pi, which is 180 degrees. So, sin 180 will be 0, and this is 3 pi by 2, which is 370 degrees. At 270 degrees, we can say that the sine value will be minus 1. So, this corresponds to minus 1. So, this is plus 1, and once again sin 360, which is 2 pi, will be 0. Clear? So, this is how the sine curve looks like, and similarly cos curve would be something like this. So, you will be looking at these curves from now onwards most of the time. So, we will be dealing with these functions many a times. So, you should definitely know how the graphs will look like. So, you can see that at 0, which is cos 0, the value will be 1, cos 90, the value will be 0, and once again 180, the value will be minus 1. We have used this result in the earlier question, right. So, at 180 it will be minus 1, at 180 this will be 0. Okay. So on, you can understand that from the graph. Okay. Now, let us see what will happen if I find area under the curve. So, for example, let us say I need to calculate this area. So, I need to calculate this area, right. So, we have just done this earlier, right. So, in this general case also, let us quickly derive that. So, it will not take much time, right. So, let us say I need to find that area. I can find that area by writing this expression, integral sin x dx, because I need to find the area between 0 and pi. I will substitute the limits as 0 and pi. Clear? So, now when I integrate this, we have seen just earlier that I will be getting minus cos x, and when I substitute the limits as 0 to pi, what do I get here? So, this will be equal to minus of cos pi, which is minus 1, minus cos 0, which is minus 1, and solving this will give me the value as 2 units, correct. So, which means if the peak of this goes till 1, then this area will be equal to 2. Clear, students? Okay. Now, let us try to find out what would be the area, this as well, I mean the whole area which I have shaded now from 0 to pi, this area plus this area as well. So, let us try to calculate that. So, which means I am just going to change the limits, right. So, I need to find area under the curve from 0 to 2 pi, correct? So now let's see what will I get by doing that. So we can easily say that the graph would look similar on above the x-axis as well as below the x-axis. So if this area is 2, this area should also be 2, correct? Which means 2 plus 2, I should get 4. So let's see whether I am getting 4 or not. So when I integrate this, the same term minus cos x I would be getting, and if I substitute the limits, this would be 0 to 2 pi, right? So this will give me minus of cos 2 pi minus cos 2 pi minus cos 0. So cos 2 pi, which means cos 360. So cos 360, the value of that is same as cos 0. So this is something which most of you would have known. Even if you have not known, remember that 360 degrees and 0 degrees are one and the same, because for example, let's say if I have this as my coordinate axis. So if there is this one which represents 0 degrees, so if this is 0 degrees, let's say, you know that angle is always measured with x-axis, right, with the positive x-axis. So if I ask you what is this line making with x-axis, what is the angle that it is making with x-axis, you will easily say that it is 0 degrees, because it is along the x-axis. Now if I tell you that this line has travelled like this, it has travelled like this, it has travelled 360 degrees, and once again it is like this. So is there any difference between these two lines? Whether it has not travelled any angle or it has travelled by 360 degrees and it is now in this direction, it does not make a difference, right? It is still making an angle of 0 degrees with x-axis. So that is why we can say that whether it is 360 or 0, both are the same angles. Clear? Okay. So based on that, can I say that cos 360 will be 1 minus cos 0 is also 1. Now if I simplify this, I am getting 0. Now this is very, very important, right? So why am I getting 0? I should get 4, right? So the value I should get here, because this is 2 and this is 2, I should be getting 4, but this integration here is giving me the value as 0. So why is it so? Okay. So the reason for that is something which we called as signed area, right? Sign, which means for area we should associate a sign as well. So in this particular scenario, what happens is that this is the area above the x-axis. So this is considered as positive area, and this is the area which is below the x-axis. So this is considered as negative area, and that is the reason when we are integrating from 0 to 2 pi, so we get plus 2 plus minus 2, which will become 0. So that is why we are getting that result over here. So remember that definite integration, so this is a point which you should definitely keep in mind. Definite integration gives the signed area under the curve, Clear? So this cos function is also something which is similar to sine function. The only thing is that if you see, if I just extend this further backwards like this, it looks like this, right? So instead of looking the graph from here, if you are looking the graph from here to here, it looks exactly like a sine curve, which means if this curve is slightly shifted like this by 90 degrees, you will be getting this curve. Clear? Okay, you will learn about this once you start trigonometry. So this is not required for us now, but what I am trying to say is whatever is this area under this dome, so this dome like structure, whatever is this area, same will the area be for this dome like structure, but because it is below the x-axis, we can say that this area will be minus 2. Clear? So based on that, you can easily answer the values of integral. For example, if I ask you in this particular case, what is the integration of cos x between, this is pi by 2 and this is 3 pi by 2, right? So between pi by 2 and 3 pi by 2. So what should be the answer for that? What is the answer for this? Between pi by 2 and 3 pi by 2, what is the area under cos x graph? What is the area that cos x graph forms with x axis? So it is this area. and we know that the magnitude of this area will be 2, but because it is below the x axis, we can directly write the answer as minus 2. Or if they ask you something like this, what is the integral of cos x dx from, let us say, 0 to pi. So, this is pi, right, 180 degrees. So, which means I am asking you to find the area between this line and this line. So, between these two lines, what is the area enclosed by cos x curve? So, that is what we are finding out. So, from 0 to pi. So, what will be the answer for this? You can easily tell the answer now, right, because you can easily say that this area is positive area and we have the same amount of negative area here. So, without even calculating, by looking at the graph itself, we can say that this answer should be 0. Clear? So, that is the idea, students. And you may get a doubt, why am I assigning sign to the area? So, why can't I just integrate that, or why can't I just calculate the magnitude of area? Why am I putting a sign for that area? See, the reason is what we are doing here is basically integral of y into dx, correct? Integral of whatever that y is. Here it is sin x, here it is cos x. So, we are basically performing this operation, right? Now, in this particular scenario, you can say that the y value, for sometimes it is positive, for sometimes it is negative. So, wherever y is positive, you will get a positive value for this, and wherever y is negative, you will get a negative value for this, correct. So, that is the reason y is negative in this region. So, whenever you are integrating between these 2 points, you will definitely get a negative area, because it is just a mathematical term, right. So, this is negative, which means the overall value will become negative in that scenario, right. So, that is the basic concept behind this. So, whenever you are integrating a function, please keep in mind that you have to you are calculating the signed area in the sense above x axis positive, below x axis negative. So, sometimes just by looking at the graph, we can easily tell the answers, so without even calculating. So, even in this question, if they ask you what is the area under the curve for cos x between 180 degrees and 360 degrees. So, you can easily say that it would be 0, right, because this is negative area, this is positive area. But if I ask you the same thing for sine function, what is the area under sine function between 180 and 360? Will it be 0? No, it will be minus 2. But for cos function, it will be 0. Clear, students? So, that is the basic idea. So, by looking at the graph also, sometimes you can get an understanding of what an integral value should be for a given function, right. So, students, now we will discuss about something called integration by substitution, right. So, see, in differentiation also we learned about something called chain rule, right. Whenever we have function inside a function, we know how to differentiate it. So, we can replace that whole thing inside a function with something, we understood it as smiley. We will first differentiate that function with respect to smiley, and then differentiate smiley with respect to x or t or whatever that they are asking us, correct. So, now this is something similar to that, but initially we will be learning it by pure substitution, clear. Then we will understand it by using the concepts which we understood in chain rule, right. Okay. So, let us see. We will directly take an expression to understand it. So, let us say we are asked to find the integral of some x plus 5 whole square dx, right. So, we know how to integrate x square with respect to x, we know how to integrate 5. So, but here they are asking x plus 5 whole square into dx, correct. Okay, you may say that I will directly expand this into let us say I will use a plus b whole square formula, I will expand this, I will get 3 individual terms, I will integrate the 3 separately. Yes, you can do that, there is no mistake in that, you can definitely do that. But what if I give you, instead of 2, if I give you let us say 199, will you expand it then also? You can't, right. So, we need to have some other method for doing such cases. So, which is what we are learning now. So, we will start with x plus 5 whole square, we will do that 199 also if you want, right. So, x plus 5 whole square dx. So, what I am going to do now here is, so whatever is present inside the bracket, we know that we have identified that this is in the form of a function x plus 5 inside another function which is whole square, correct. So, I will replace this inside term which is x plus 5 with a variable t. I will assume some variable, you can use any variable. So, if you like some other letter, use that letter, it need not be t. So, t is equal to x plus 5, clear. So, now as soon as I do that, I will see that this becomes t power 5, but t power 5 I have dx here, right. I can integrate t power 5 with respect to t. I do not know how to integrate t power 5 with respect to x. So, what should be our next step? Somehow replace this dx with dt. Do you understand what I am saying? I need to replace with dt. Okay. Replace in the sense, do not just remove dx and substitute dt here, that is not what I mean. I need you to find the relation between dx and dt and use it here. Do you understand that? What I am basically doing is converting this function in x, this expression in x into an expression in t, because if I am converting it into t, it becomes the basic integral form, right, which we know the formula for, correct. So, that is what I am doing here. Now, I need to replace or find the relation between dx and dt. How do I do that? We already have this expression, correct. So, I will just differentiate this, because I need dx and dt, right. How else can I get? By differentiating this function, correct. So, when I differentiate this function, let us say I am differentiating it with respect to x, which means dt by dx. So, I am or you can understand it in this manner. So, what I am doing here is I am doing d by dx on both sides. So, I have t is equal to x plus 5. So, t is equal to x plus 5. So, what I am doing is I am putting d by dx on both sides. Clear, students? So, from this I will be getting the value of dt by dx as, what is d by dx of x? You know that it is 1 plus, what is d by dx of 5? It is 0, right. So, that is it, this is equal to 1. So, which means dt by dx is equal to 1. So, we can write dt is equal to dx, clear. So, remember that dt is equal to dx only in this scenario, not all the time. What if I have given 2x here? If it was 2x here, then I would be getting 2 here, right. So, do not think that dt is always equal to dx. So, in this case it is equal to dx. So, let us get back to this. Okay. So, I hope this is clear. Now, I will replace this dx with the relation which we have here, and this expression will now become a very simple integral, which I know the integration of. What is integration of t power 5 dt? So, we can directly use the formula, which is t power, we need to increase the power by 1 in the numerator, in the power, and divide it with the same value. So, t power 5 plus 1 by 5 plus 1 plus c. So, do not forget this c, we are doing indefinite integration, correct. So, this is equal to t power 6 by 6, right. What is t power 6 by 6? If I replace the value of t back to our original expression which we assumed, so this will automatically become x plus 5 whole power 6 by 6 plus c, correct. So, that is it, students. So, that would be the final answer for that, clear. Now, as I asked you earlier, what if this was 199? So, let us say x plus 5 power 199 dx. Let us not take x plus 5, let us this time take some 3x plus 5. Okay. So, 3x plus 5 whole power 199 dx. So, how do we integrate this? So, once again the method is same. I will replace this term which is inside the bracket with some t. So, t is equal to 3x plus 5. So, this will automatically become integral of t power 199 dx. So, once again the same problem, I can integrate t power 199 with dt, not with, with respect to t, but not x. So, what am I going to do? So, this is, okay, let me write it down. First, let us find the relation between dt and dx, clear. So, we know how to do that. I will differentiate this with x on both sides, So, I get dt by dx is equal to d by dx of 3x. You know the value of that, right? What is the derivative of 3x with respect to x? It is 3. And what is the derivative of 5 with respect to x? 0. So, that this would be the relation, which means from here I would be getting the value of dx as dt by 3. Clear? Now, you will just have to replace this dx with the result which we derived here. So, this becomes integral of integral of t power 199 into dx is dt by 3, right. So, just this is simple integration now. So, 1 by 3 into t power 199 dt. So, t power 199 dt will be t power 199 plus 1 by 199 plus 1, which is 200 plus c. So, the final answer, if I replace the value of t with the value which we assumed, so the final answer which I would get is 3x plus 5 whole power 200 by 3 into 200, which is 600 plus c. See, very simple, right? So, that is the idea. So, whenever you have functions like this, you just try to replace the term which is inside with a variable and try to simplify from there. So, it will be very easy to solve. Clear? So, we can also take one more function. Let us see one more example. So, this is second. So, let us see another example. So, this time let us take integral of sine 2x dx. Clear? This is sine 2x dx. So, we need to integrate this. So, once again the same problem. I know how to integrate sin x with respect to x. I do not know how to integrate sin 2x, right? Correct? So, what am I going to do now is once again the same. In my mind, I will think like this. First, initially we will be practicing it like this by substitution, but you will observe that after a while we can do all this in our mind, like we have done in the case of differentiation in chain rule. Clear? So, t is equal to 2x, right? Now, I will differentiate this. I will get dt by dx is equal to 2, which means dx is equal to dt by 2. Correct, students? So, dx is equal to dt by 2. Now, I will write this whole function in terms of t. So, this becomes sin t into, in place of dx, I will substitute dt by 2. And now we know how to integrate this function, right. So, 1 by 2 I will bring it outside. So, 1 by 2 into integral of sin t is minus cos t. So, minus cos t plus c. Clear? Now, bring back the value of t from what we have assumed. So, this will finally give me minus cos 2x by 2 plus c. Clear? So, that is the idea. So, wherever we have functions like this, so just assume it as some variable and perform the integration, right. Students, we will see a few more examples based on the substitution method, right. So, this is the first one here. So, 1 by 5x plus 7 whole power 4. So, whatever it is, I will just assume it as t. So, if I assume t is equal to 5x plus 7, so I need to replace this dx. So, I will directly differentiate this. I would be getting dt by dx is equal to 5, right. So, now I will write the whole expression in terms of t. So, this becomes integral of 1 by t power 4. You all know that 1 by t power 4 can be understood as t power minus 4, correct, into dx. What is dx from this relation? I can write dx as dt by 5. So, dt by 5. Clear? Now, we can easily integrate this. So, I can bring 1 by 5 outside. So, we have t power minus 4 dt. So, which is t power minus 4 plus 1, which is minus 3 by minus 3 plus c. Clear? So, solving this will give me minus 1 by 15. So, bring back the value of t, which is 5x plus 7 power minus 3 plus c. So, that should be the answer. Simple, right? Okay. So, this is a similar term, A and B are constants here. So, a general expression basically, not they have not given any numbers. So, they have just taken some constants A and B. Okay, whatever it is, I will assume this whole thing as a constant, a variable t, which we usually do. So, t is equal to Ax plus b, correct. So, once again dt by dx. So, dt by dx is equal to what do I get? If I differentiate Ax with respect to x, remember A is a constant. So, that is nothing but A into d by dx of x, right. So, A into d by dx of x is 1. So, A plus derivative of b will be 0 because b is a constant. So, that is it. I will be getting A, which means dx is equal to dt by A, correct. So, now when I substitute that here, I would be getting 1 by Ax plus b can be replaced with t into dx. Dx is nothing but dt by A. So, now this is a simple integration 1 by A into integral of dt by t. So, you know this, right? What is dt by t integral? It is nothing but ln t. So, I will be getting this as 1 by A into ln t plus constant. So, now you can replace this t with the value which we have there, which is Ax plus b, clear. So, that should be the answer. Okay. Now, moving on to the next question. So, if you see here, so this looks very big, right. So, e power x square plus 3x plus 1 into 2x plus 3 into dx. So, although it looks very big, the method is the same. It is very easy to answer this also, you will see. So, I will obviously consider this whole term in the power of e as my variable. So, let me first do that. So, I have t is equal to x square plus 3x plus 1, right students. So, now what do I do? If I differentiate this with respect to x, I would be getting dt by dx is equal to, what is this value here? 2x plus 3, correct. So, that is the expression which we would be getting. So, do you understand this? Normal integration, normal differentiation with respect to x. So, dt by dx is d by dx of x square, which is 2x, d by dx of 3x, which is 3, d by dx of 1, which is 0. So, this is the expression which we would be getting. Now, I will have to replace, I will have to use this expression to eliminate dx. So, what is this expression going to get converted into? E power, this whole term we have assumed it as t. So, e power t into, now observe carefully what we have here, dt by dx is this value, correct, which means I can write dt is equal to 2x plus 3 into dx. So, I just send dx this side. Now, whatever term which we have here is same as this term. Do you identify that? So, which means I can replace this whole parameter with what? dt, that is it. So, this whole parameter will become dt. So, when I simplify this, we know the integral of e power t, it is very simple, it is e power t itself. So, e power t plus c. Now, you can bring back the value of t which we have in that expression. So, this becomes e power x square plus 3x plus 1 plus c. So, that should be the answer. Clear students? So, although it looks very big, so if you identify that, if you observe closely, the derivative of this is this expression, right. So, that is the reason it has become very simplified. Clear? Sometimes if they do not give the derivative of this function as this, then it will be a very lengthy process which you will only learn in your mathematics class by using something called as integration by parts. So, you do not have to worry about that now, you will not be given cases like that also, right. Only cases where the derivative of this is also written here. So, in such a case it gets simplified into a very simple expression which you can easily integrate. Clear? So, for us in physics, we would only require very simple integrations, we do not need complex integrations, right, you do not have to worry about all that. So, these basic integrations would be enough for us. So, students, now let us understand the concepts which we learned earlier in a slightly different way. So, what I am going to tell you now is something which is applicable for functions which are in this form. So, let us say ax plus b. So, f of ax plus b. So, it could be any function which is in this form. For example, let us say if I have f of x is equal to x power 4, then f of ax plus b, this would be ax plus b power 4. Clear? So, something which is a function of a linear term ax plus b. So, if whenever we have functions in this manner, so the integration of these will be very easy. So, I will show you how. So, for example, let us say I take 7x plus 11 whole power 4 dx. So, let us say this is our expression which we need to integrate. So, now, so remember the Smiley replacing method which we discussed in differentiation, right. So, we can do this by a similar method. So, what I can do is, so I will forget whatever is inside, I will understand that as a Smiley, right. So, this becomes integral of, so this becomes integral of Smiley power 4, right. So, Smiley power 4, but if I have to integrate this, you know that I can integrate this if there is a d Smiley here, then I know how to integrate that. So, what I will do is I will just multiply this with a d Smiley and also divide with a d Smiley, which means effectively I have not done anything new. These two will get cancelled and the same dx I will be writing here. So, understood. So, I have just replaced this with some Smiley, I am viewing it as a Smiley and I have multiplied and divided that with d Smiley. So, now in this particular scenario, if you observe, so I can write this as integral of Smiley power 4 into d Smiley divided by, right, divided by, this integral will be for the whole thing. So, integral of, so this dx I will take it to the numerator, sorry, denominator. So, this will eventually become d Smiley by dx. Clear, students? So, this is the expression which we will be getting. So, please observe carefully, I have not we have not done anything extra here. So, here d Smiley and d Smiley will get cancelled out and dx will be in the numerator. So, that we will be getting back the same function. So, I have just rearranged it in a slightly better form. Clear? Now, if you observe this, if I assume that my Smiley is this expression, can I clearly say that d Smiley by dx, the value of d Smiley by dx in this case is nothing but 7, correct? It is nothing but 7 in this particular case. So, this becomes a constant, right? And because this is a constant, I can bring this outside the integral, correct? So, this becomes 1 by 7. So, d Smiley by dx will become 7 and this will be integral of Smiley power 4 d Smiley, and this is something which we can easily integrate, correct. So, this will be equal to 1 by 7 into, this is what, Smiley power 5 by 5. So, solving that will directly give me 7x plus 4 power 5, sorry, plus 11, right. So, plus 11 power 5 divided by 5. Clear? So, this is how we can solve this. So, whenever the function is in the form of ax plus b. So, remember that this d Smiley by dx will be a constant term only for such functions. Clear? So, that is why I have told you that before itself, only in such cases this will be a constant, I can bring this outside and integrate this expression. Clear? So, you can understand it that way. So, I will give you another example for you to get a better idea. So, let us say we have this function sine of 2x plus 5. So, let us say this is the function which we need to integrate. So, if I apply the earlier concept which we have discussed, so I will understand this as Smiley. Instead of integrating this with x, I will integrate it with respect to Smiley. So, which I can easily do, right. So, whatever is inside this, I will not even look inside that. Clear? This is sine Smiley, I will integrate with Smiley. So, what will I get? I will get minus cos Smiley and the value of that is 2x plus 5, correct. Now, the question is not over because I have integrated this with respect to Smiley. Then what is the next step? I will have to divide it with d Smiley by dx. And what is the differentiation of this Smiley with respect to x? It is 2, right. So, plus c, that should be the answer. See, the only difference between what we did in differentiation and here in integration is, see, if the same question, if I ask you to differentiate, d by dx of 2x or sine 2x plus 5. So, if I asked you to do this, what will you do? You will consider this as smiley, first differentiate that, you would get cos 2x plus 5, then what will you do? Then you will differentiate the inside one, right? What is the differentiation of the inside part? 2. You will multiply that here. Here you will divide with that. That is the only difference. Clear? So, here you will be multiplying it with 2. Correct? In this case, you will be dividing it with 2. The rest is all the same. You will integrate that first function, then you will differentiate the inside term and then divide with that in this particular manner. Is that clear, students? So, I will give you a few more examples based on this. So, let us see. So, for example, let us say we have integral of cos 7x plus 9 dx. So, once again the idea is same. So, first I will integrate this expression without even looking at this, clear. So, cos of anything, when I integrate that with respect to the same thing, what will I get? So, the cos function when integrated gives me sine function. So, sine 7x plus 9, correct. Now, what should I do? I should differentiate the inside part, and whatever I get, that I will be putting in the denominator. What will I get by differentiating this with respect to x? I will get 7, correct. So, that is it, plus constant. Is that clear? So, that is the basic idea of understanding such cases, but remember you can use this method whenever you have this in this form, ax plus b form, right, students. So, we will see few more. So, students, let us take one more. So, this time let us say integral of 7x or let us say some 3x plus 5 power minus 3 dx. So, once again please observe how I am approaching this. So, I am not looking at what is inside, whatever is inside. So, power minus 3, when I integrate that with respect to the same term which is inside, what will I get? So, I would be getting 3x plus 5 power minus 3 plus 1 by minus 3 plus 1, which is minus 2. So, I did not even look at what is inside, you can forget about what is inside. I will first apply the derivative of x power n, right. So, that concept I will be getting this expression, correct. Now, what should I do? I will differentiate the inside term with respect to x, correct. When I differentiate the inside term with respect to x, I get 3. Now, I will just divide that with this expression with 3 plus constant. So, that is it, simple, right. So, minus 1 by 6 into 3x plus 5 power minus 2 plus c. So, you will have to do a little bit more practice on such types, clear. So, at first it might seem too much to understand, but it is a very simple concept, you do not have to worry. So, let us quickly see one more example. So, integral of let us say x plus, or let us not take x, let us take some 8x minus 1 or minus 8x minus 1 power minus 1 dx. So, this is the idea. So, let us solve for this, clear. So, now if you observe closely, so here we have this particular term, right. I have told you that whenever the power is minus 1, when you integrate that you will be getting a ln term, right. So, this, you remember this integral of 1 by x into dx is ln x, correct. So, it is ln x. So, in this particular scenario, when I integrate this particular expression, so what will I get here? So, I will not look at what is inside, correct. So, if you want you can write this as 1 by this value, correct. If you want you can take the minus sign outside, if you can bring it out, let me bring that minus sign outside. So, when I bring that minus sign outside, this will be 1 by 8x plus 1 dx, correct. Okay. Now, as I told you, I will not look at what is present inside. So, this is in the form of 1 by x dx, right, it is in that form. So, when I integrate this expression, I will be getting ln x. So, minus ln 8x plus 1, but it is not over, because we once again have to differentiate this inside term and then divide with that, clear. So, when I differentiate this inside term alone, which is 8x plus 1, what will I get? With respect to x, if I differentiate, I get 8. So, whatever we got earlier, I will just divide it with 8 plus c. Clear? So, this is something similar to chain rule. In chain rule, we will be differentiating the inside term and multiplying with that. In integration, we will be dividing with that. Clear? So, that is the idea. So, students, now let us see some applications of integration in different cases which we generally use. So, like calculating the area of a circle and finding the volume of a given object. So, for all these we can actually use integration to do that. So, let us see few examples. So, first let us derive the area of circle by using integration. So, you all know the area of circle, the value of that is basically pi r square if you take a circle of radius r, correct. So, I am not going to tell you something which you do not know, right. I am only going to show you how to use integration to understand this result. How should integration be applied for cases like this in a real case scenario, clear. So, how is integration useful for us? So, if I learn it from the basic, if I am able to do it for a circle, then we can take it to a sphere, then we can take it to a complex shape, and we basically will get an idea of how integration can be applied in different cases. So, that is the reason why we are doing this, not because you do not know the area of circle, right. So, let us see. So, I have a circle, you can consider it to be a disc, clear. So, let us say the radius of this is capital R. Now, so whenever we need to use integration for calculating, in this case I am trying to calculate its area, right. So, remember earlier we discussed something like this. So, what does this integral operator do? So, this integral operator has only one role, it can perform infinite number of additions, correct. So, if you put a term here, if you give it a small term beside that, what it does is this operator looks for parts like this and it will take all those parts and it groups all of them together and give you the value. So, that is what this operator does. So, by using that operator, I am now going to find the area of this circle, but like I told you, we need to give it some inputs. So, what are the inputs I should give that operator? I need to tell it what to add, correct. So, if I have to find the area of this circle, we need to tell the operator. So, I need to give the input to the operator which is what to add. So, unless and until I tell it what to add, it can't do that operation, right. So, first I will have to decide. So, how should I break down this circle, how should I view this circle and take a small part in that circle, find the area of that and then give that area to the operator. What will the operator do? It will look for many such areas and bring all of those together, clear. So, you will understand as I explain this. So, what I am going to do here is, I am going to view this circle, clear, this circle or the circular disc as a combination of many rings. So, please listen carefully. I am taking this circle or circular disc as combination of many rings of varying radius, clear. So, which means, so let us say if I consider this as r and the thickness of this as dr. Now, think of a scenario, if this is one of the rings which I have considered, clear. So, just consider one more ring which is just outside it, slightly bigger radius, clear. So, just another ring outside this of similar thickness, take another ring outside that of similar thickness. So, what I am saying is, I can create a disc by considering or by taking rings of very small thickness and increasing radius, clear. So, what I am trying to say is, if I bring together, first let us say I have taken a small ring like this, right. So, I have taken a small ring, outside this ring if I place one more ring which is having slightly higher radius, if I place one more ring of even slightly higher radius, another ring of slightly higher radius, and so on and so forth. So another ring, another ring, another ring. So if I keep increasing the radius of those rings with the same thickness, can I say that this will eventually become a disc? Do you understand that? So that is what I am trying to say. So I have taken a ring of radius r and thickness dr, and what I am saying is, if r varies from 0 to capital R, if r varies from 0 to capital R, which means I am starting with a very small ring of almost 0 radius, which would be the one which I started here with. So a very small ring of almost 0 radius, then I will put another ring of slightly larger radius, as I have told you here, till where? Higher ring, higher ring, higher ring. So till where am I doing that? Till I reach a radius of r. So what am I going to get? I am going to get a circle of radius, I mean a disc of radius capital R. So that is what I have written here. I can create a disc by taking rings of very small thickness and increasing radius. So one ring will be like this. Outside that there will be another bigger ring, another bigger ring, another bigger ring, another bigger ring, and it will eventually become a disc. Correct? So that is how I am viewing it. Clear? Now what I am going to do is, I am going to find the area of this ring. So the one which I have shaded here. So I am going to find the area of this shaded part. Now you may ask, how do I know the area of that? Now it is very easy to understand the area of this. So please observe closely. What I am going to do is, I am going to bring this ring outside. Clear? I have a ring now. Clear? I have a ring here. You know the circumference of this ring? How much will be the circumference of this ring? Or let me draw that here. So now this is our ring. So I have separated this ring from our disc. So this is the ring which I have. Okay. So now this ring has a radius of r and a thickness of dr, correct? Okay. Now I know the circumference of that ring, which is 2 pi r, that we all know. I have already told you that the circumference of, okay, we will be using this result basically. Circumference of a circle will be equal to 2 pi r. That is something which you already know. I will be using this result to derive the area of this circle or the area of the disc. Okay. Now if you look here, if I consider this particular ring, if I have to find out this area, what I am going to do is, I am going to cut this ring at one position. So let us say I am cutting it here. So if I cut it here, now after cutting it here, now I am going to spread this in this manner. Clear? So when I spread it, so this becomes a strip like this. Able to follow that? So what I have taken is, first from this disc, I am viewing this disc as a combination of many rings of increasing radius, and out of that I have taken one ring separately, and I am trying to find the area of that ring, right? And the area of that ring, how am I calculating it? I have first cut it and I have spread it into a strip, right? And you understand that this strip here is nothing but a rectangle, right? So this is nothing but a rectangle. It looks like a rectangle, right? And you can easily say that when I am spreading it in this manner, whatever is the length of this ring or whatever is the circumference of the ring is what is getting spread as length of the rectangle S. So which means the length of this rectangle here will be 2 pi r. Clear, students? And what will be the thickness of this rectangle or what will be the width of this rectangle? That will be same as the width of this strip, right? So the width of that strip would be dr. Understood? So which means I can now say that the area of this strip can be understood as 2 pi r into dr. So that is the expression for elemental area. We call this as elemental area. So elemental area means the area of the small part which you have considered in that disc. Is that clear? So I have taken an element like this, I have chosen an element like this, and I am finding the area of that element. And what is the method which I used? I have cut that ring, I have spread it, it becomes a rectangle, I can find the area of rectangle. Simple, right? Okay. So, now this is the area 2 pi r dr. Now, what should I do? Now, I should tell the operator that see this is my elemental area, which means I have taken a ring and the area of that ring is this much. So, now what you do is, so take many such rings. So, take many such rings of 2 pi r dr areas, add all of them and give me the answer. So, if you ask this integral sign, it will do it for you. Okay. So, first what you will have to do, what we will have to tell that is give this input. So, 2 pi r dr. So, first you will have to understand what is the elemental area and give that elemental area to the integral operator, and that integral operator will add all of those rings for you, which means it will take the area of this ring, it will look for a similar ring of bigger radius, it will look for similar ring of even bigger radius, similar ring of even bigger radius, and all those areas will be added by this operator. Clear? But you will have to tell from where to where it has to add, correct? Otherwise, this operator will not give you a value, right? So, if you tell it from where to where, you will have to add those rings, then it will perform that operation for you. That is it. So, this will be the final answer. So, you will see this is equal to 2 pi is a constant. So, 2 pi into integral of r dr. And what is integral of r dr? R square by 2, correct. So, 2 pi into r square by 2. Now, if I substitute the limits as 0 to r, I would be getting 2 pi into, you can bring this 2 outside, into, when I substitute r, I will be getting r square, when I substitute 0, I will be getting 0. So, that is it, 2 and 2 gets cancelled and the final result would be pi r square. Clear, students? So, that is the basic idea. So, if you observe closely what we have done. So, first we understood this disk as a combination of many rings, correct. So, I have viewed it as a combination of many rings. So, as you can see here, so I have taken it as many rings. I have found the area of one ring by myself, clear. So, this is the elemental ring, we call it as elemental ring, correct, elemental ring you can say. Okay. So, we have found the area of that by myself and I am telling the integral to add such areas from 0 to r, and it will add all such areas and finally give the answer as pi r square, clear. So, that is how we use integration. So, in the same manner we can use integration for different other cases also. So, we can use it for calculating the volume of sphere, volume of cone, you know these formulas, right. Volume of sphere is 4 by 3 pi r cube, correct, and volume of cone is 1 by 3 pi r square h. So, all these you have understood these as formulas till now, correct. You have been studying about that in your lower classes, but you only remembered those as formulae, correct. But now we are going to derive that also, but we will do that in next class. So, in this class the time won't permit us. So, just try to get an idea of what we have done here. So, understanding this idea is very important, the result is something which you already know. So, look at what we have done here, how I have understood that disk, how I have constructed that disk by using many rings. So, try to visualize that scenario, small ring, slightly bigger ring, slightly bigger ring, slightly bigger ring. If I keep adding those in that manner, it eventually becomes a disk. So, find the area of one ring and give it to the integral sign, it will do the rest. Clear, students? Okay. So, in next class, as I told you, we will calculate the volumes of different objects and try to apply integration in different other concepts as well. Clear?